Thank you for joining the meeting. This morning I'll be talking to you about some new processors that Mike said we're announcing today. And these are designed to deal with some of the challenges that we're seeing that embedded designers are facing as in the development of very high performance embedded products today. So a few years ago, it used to be that every time we moved to a new process node, you would see roughly twice the clock speed capability, half the power consumption, half the cost as well. Which is nice. That, of course, has gone away for some time. Logic speeds, the chart on the left there is showing you that logic speeds for many years have been increasing at a much faster rate than memory access times. In fact, when we step into new processes, at least initially, the memory access times slow down a little bit, and then they seem to catch up, at least to where we've been. But that creates other challenges, usually the critical paths now through the processor that limit clock speed are through the memories. Hold on a second. And also, one of the other things we're seeing in embedded is that the maximum clock speeds that people are clocking the devices at is in the 1 to 2 gigahertz range. We're not really seeing clocking requirements above that for embedded. Of course, we do see that for PC processors and for cell phone application processors, but we're not seeing that at all for in embedded applications. And that's primarily because of limitations in power consumption as well as limitations in cost. Now, at the same time, all this is going on, and that's, by the way, what the chart on the right is showing you. At the same time, while all this is going on, the need for higher performance in the processors and the devices is increasing because of competition, because of increases in functionality, changes in features, and advances in features that are driving the performance requirements up. So, as processor designers and developers, we've implemented a number of things to help you in that regard. First of all, we built deeper pipelines, and that really doesn't increase performance. In fact, if you don't do it right, it can reduce performance. But what it does do, it allows the processor to be clocked at higher speeds, which today, like I said, in embedded are running in that 1 to 2 gigahertz range. And that's primarily because we're allowing more cycles for memory access. So you can deal with the slower memory access time versus the faster logic times. With the HS processors, ARC HS processors, we have 2 cycles for memory access that allows the processor to be clocked at twice the speed of the memory. So you could run the memory, for example, at 1 gigahertz and run the processor at 2 gigahertz. We've also added capabilities like superscalar architectures or multi-issue capabilities. We have that with the HS cores with 2 issue. In fact, when we looked at this, we see with a 2 issue or being able to execute up to 2 instructions per clock, you get about a 40% increase in RISC performance. But that's at the cost of about 20% increase in power and area, which is actually a good trade-off. But when we go beyond that, we see the trade-off is less beneficial. Now, multi-threading is something which really hasn't been used a lot in processors that are used in embedded applications. That's because, for one, it's from a hardware standpoint, it's complex, and 2, it adds a lot of hardware compared to the performance you get. Out-of-order execution, OOO, is something that's used especially for out-of-order completion. We have that capability in the HS processors, and it definitely increases performance. Of course, caching has been widely used for many years. L1, level 1, level 2 caches have been widely used. We're starting to see actually customers needing level 3 cache in embedded designs. That's really only previously been used in PC servers and cell phone application processor. Of course, caching is much more efficient with coherency, which we have in the HS processors. Now, one of the things that has started to change and will continue to change as we go forward is having wider bus interface structures. Currently, well, a few years ago, most of the buses were 64-bit or maybe 128 bits wide. Today, we're seeing those bus widths go to 256 and even 512 bits widths to allow the user to move the data in and out of the processor at a high enough speed so that you don't choke off the processor. Now, another thing that's being done is implementing wider pipelines. We've seen a lot of movement towards 64-bit today. Interestingly, increasing the pipeline width from 32 to 64-bit without doing anything else to the pipeline doesn't really increase performance. It does allow you to access a much larger space. It can also support higher bandwidth through the processing unit. But for general benchmarks, it doesn't do a lot. Even so, we're seeing a movement towards 64-bit primarily for the larger address range. Now, a couple of things that we're seeing a lot, been getting a lot of requests for in the embedded space is multi-core implementation. We've had up to 4-core capabilities with the ARC processors for years. We're seeing requests beyond that. And in addition, requests for hardware accelerators to improve performance and lower power consumption. Now, these are the new processors that we're announcing, the HS5 and HS6 cores. The HS6 cores are 64-bit. They have a full 64-bit ALU and pipeline and core registers. They will support 64-bit virtual and 52-bit physical address spaces. That 52-bit physical address space is 4.5 petabytes. That's 4.5 times 10 to the 15, or if you want 45,000 terabytes of data, which is a lot. It's more than customers need today, but we're always forward-looking, asking the question, what's going to be needed in the future? And I think we can get there pretty quick. These processors also support 128-bit loads and stores per clock, so you can move data around the processor very quickly. The HS5 cores are 32-bit. These are all 10-stage pipelines. That's a very efficient pipeline that we developed specifically for embedded applications to maximize performance while minimizing power and area, which is so critical for embedded. This is a dual issue pipeline, so we get advanced in performance. Now, one of the capabilities that we've added to these processors is the ability to scale up to 12 CPU cores, and in addition, up to 16 hardware accelerators. So you get very scalable performance, so you can meet the high performance requirements of your specific workload. They also support up to 16 megabytes of L2 cache, and that's inside the processor cluster. And we, of course, have support for Linux and the Zephyr RTOS and quite a range of development tools to support these processors. Now, these are some of the capabilities I've mentioned, the 12-core clusters with 16 accelerators. The cores can be clocked up to 8.5 gigahertz, 1.8 gigahertz, worst case, and 16 nanometer process, of course, faster and finer geometries. We fully redesigned the interconnect to maximize the bandwidth internally inside of the processor. These processors support 800 gigabytes per second aggregate bandwidth internally. So you can move data around as needed, and none of the processors or cores being used inside of the processor cluster will be stalled. We also have quality of service scheduling, so the user can schedule the amount of interconnect bandwidth that's allocated to each of the cores. And we have, in addition to the L2 cache, up to 16 megabytes of shared cluster memory that allows, under software control, information to be moved around inside of the cluster or into and out of the NOC. Now, these cores, all the cores in the cluster are supportive of multiplex source synchronous interface that can be fully asynchronous or synchronous. It's up to you. You can manage it on a per core basis. They also all run in their own power domain. And this allows first of all, power to be managed very specifically by the user. But it also allows the clock tree to be minimized so that you can maintain tighter skews as well as meet higher clock frequencies in a large multi-core cluster. And then finally, as I said, we've fully redesigned the interconnect to reduce, increase the performance and bandwidth, but also to reduce the wiring inside of the cluster. Now, all of these processors, as I said, are designed for embedded applications. They have a lot of features targeted specifically for embedded applications, like the ability to individually read and write any register on an SoC, which reduces latency and increases performance. They have up to 16 megabytes of close coupled memory. That's single cycle access memory that's tightly coupled to the processor. That can be implemented with or without cache. It's up to you. We have support for 128-bit loads and stores, as I mentioned, for the HS6X cores. We have a custom instruction capability, which is in addition to the hardware accelerators that we have on all the ARC processors, the Apex capability that allows you to add hardware directly to the pipeline. The hardware accelerators, as I'll show you in a minute, can be added to the processor cluster. We also have support for fast context switching with up to 8 register files fully under user control and a very robust interrupt infrastructure. Now, this is a look at the processor cluster on the upper right, or upper left. You'll see the CPU cores up to 12. On the upper right are the user hardware accelerators up to 16. And then in the middle there is the interconnect. Now, this is a very highly scalable interconnect. You have a lot of control over it with, as I said, 800 gigabytes per second aggregate bandwidth, which is important. So none of the cores in this large and a very large cluster would be stalled for data. The interfaces are all industry standard. You can see the interfaces to the hardware accelerators is ACE Lite. To the NOC, those interfaces are either AXI or ACE. It's up to you. You can implement them if you want. And they're all controllable in terms of the width of the interface as well. Now, this interconnect has been designed to allow timing closure or facilitate timing closure when you implement your design with a lot of CPU cores. That can be a challenge. And we know that in many applications, but the interconnect has been specifically designed to enable you to do that and also to reduce the physical design effort. The processor support heterogeneous configuration, so you can have a mix of HS cores in the CPU space. You can have, obviously, any hardware accelerator you want to attach. You just have to attach it with an ACE Lite interface. Those accelerators, by the way, can be coherent or not. It's up to you. The data channel width for all the master and slave ports is configurable from 64 bits to 512 bits to maximize performance through the processor. And as I mentioned before, we have a quality of service capability that you can control to manage the bandwidth to each of the cores and balance the performance, especially for real-time applications. The shared cache, or the L2 cache, is configurable. It's a shared space between the L2 cache and the cluster shared memory. That's a 16 megabyte space total in size. And as a user, you can allocate that space to L2 or cluster shared memory as you need. But the size of that space allows you to keep a lot of data local to the processor, so you don't, which will reduce latency, of course, and offload traffic from the NOC. And of course, that's dynamically allocatable in real time. There's coherency between the interconnect and all the CPU cores, and also coherency between, if you want, the hardware accelerators and the L2 cache. The L2 cache can also be kept coherent with the a NOC, if you have a NOC, or memories out on the NOC, or other clusters out on the NOC. It's really up to you. You control that on a per transaction basis. There's a lot of control there for the coherency. Now, as I mentioned, all the cores can reside in their own power domain and their own clock domain, which allows you to, as I said, minimize power consumption while maximize performance. You can, run some of the CPU cores at 100 megahertz if you want, running others at a gigahertz. It's really up to you. The relationship between all of the cores and the interconnect can be fully asynchronous. It can be a one-to-n relationship, or if you want, for some reason, you can have it be fully synchronous. But what this does is it relaxes the physical design capability, makes it much easier to get timing closure, and allows you to manage more closely performance, power consumption, and area on a per core basis. We also included the capability to allow each of the cores to see the close coupled memory in the other cores. That's because we mapped the close coupled memory into a shared address space, and so that CPU core 1 could see what's in the close coupled memory of hardware accelerator 2 and make changes to it if needed. But it gives you a lot of control over how information's handled inside of the CPU cores and the hardware accelerators. Now, some of the benefits of having a larger cluster are that it significantly reduces latency inside of the cluster between the cores, allows for direct snooping, it gives you very uniform access time, and it allows for higher interconnect speeds between the cores. It also improves software scaling. You have the ability to do software-defined partitioning, so you can change the partition if you want at any time. You can have, the cores configured with 4 and 8 cores, or 6 and 6, or 3 and 9, 2 and 10, whatever you want. And you also have the ability to have, low latency coherency between all the processor cores. It's also quite advantageous for real-time applications. And of course, the integration of the hardware accelerators, one, takes all the traffic off the NOC for communication with those accelerators. And it also reduces latency between the CPU cores and the accelerators and gives the user a great deal more efficient control over the whole processor cluster. And then in summary, so these are our new, very high performance and very scalable processors for embedded applications. The HS6X cores are 64-bit, the HS5X are 32-bit. These are based on the latest implementation of the ARC ISA. We call it ARC version 3 or ARC v3. The processors are scalable up to 12 coherent HS or CPU cores and up to 16 hardware accelerators to increase performance for embedded applications and giving you a great deal more control over the area power and performance in your application, so you can balance that to maximally optimize your device for whatever application you're targeting. And of course, because we've fully restructured the interconnect, it makes it much easier to implement a multi-core, a very large multi-core structure, as well as to achieve full system integration and time enclosure. So, Mike, that's my last slide.
Thanks, Mike. Great. We'll go to the Q&A. In the time you had, you didn't get to talk about some of the things that you and I have talked about. Could you say what the different versions are that Synopsys is planning on releasing and when those will be released?
Yeah, so we already have a number of HS cores available. We've had the first, and HS core stands for high speed. We released the first of those cores in 2013. Those were single issue, and then we released a dual issue version of that in 2016, which gave us significantly higher performance than what we're announcing today are the HS5, so HS 56, 57D, and 58, which are 32-bit, but of course have support for the full 12-core CPU implementation and 16 hardware accelerators up to. And then the HS6 cores, the HS66 and 68, the 58 and the 68 have the full MMU. It's a very capable MMU, so they can fully run Linux or SMP Linux, whatever high-end OS they want to run on the processor. Those will all be available this year in September.
Okay, great, thanks. 57D, if anybody missed it, that's what DSP extension. Mm-hmm. Okay. One of the questions we have from the audience about the QoS engine. Mm-hmm. Do you think it needs some sort of a security coprocessor to make sure that the performance is secure?
So we have some secure capabilities built into this processor, but to maintain full security, we would recommend running either a hardware security block or a completely separate security processor with it. If that's an issue, the QoS doesn't have any specific secure capabilities built into it in that sense, but it does still allow for full scheduling of what happens inside of the processor itself.
Synopsys has introduced other secure cores in your
We have many, many secure cores and capabilities.
Can you do the loads and stores same time, or just 128-bit load or store?
It's 128-bit load or store per clock.
Got it.
And by the way, those can be used to move information to peripherals or in and out of memory, in and out of that cluster shared memory. It's really up to how the user wants to use that.
And you're saying that the cluster shared memory is configurable between cache and shared memory. Dynamically configurable on the fly? How does that go?
It's configured at build time. Okay. So the user decides, typically the amount of L2 cache you need doesn't change. In an application, you decide that ahead of time. You don't want to implement too much because it's a waste of space. And you don't want too little because it will increase latency, since you'll have to go to external memory. But the L2 space is configured at build time. And again, that 16 megabyte space is shared between the L2 cache and the cluster shared memory. It's up to 16 megabytes and it's user allocatable.
Okay. A question on the software support for the new cores. You mentioned the OS support.
Oh, you're asking what software support we have? Yeah, so we have full support for GNU and Linux, as well as SMP Linux for a multi-core implementation. We also are bringing up support for the Zephyr RTOS, which is an open source RTOS. In addition, we have full support with the Metaware development tools, which give you a very optimized compiler, as well as debugger and instruction set simulator. We have more advanced instruction set simulators, NSIM and XCAM, which are, NSIM is cycle close, XCAM is 100% cycle accurate. And then we have a number of development boards and as well as third-party tools that are available for the processors.
Oh, the Synopsys prototyping tools.
Oh, of course, absolutely.
Yeah. Question I have on how a designer might choose between using Apex to just install a custom instruction versus a hardware accelerator.
That's a good choice. And by the way, you have the choice now. But it really depends. I would think that if you have a very sophisticated hardware accelerator that you would think more of as a co-processor, you would probably want to implement that with the hardware accelerator interfaces, as opposed to you know, a piece of RTL that you think of more as an instruction as opposed to an accelerator. Obviously, there's a lot of overlap in those two spaces, but that's intentional. We want to give you know, the user, the designer, as much flexibility as possible to build the design they want. And by the way, the custom instruction interface is on each of the CPU cores. So you potentially could have totally different custom instructions running on each of the CPU cores inside of the cluster, as along with the hardware accelerator. So it's a complementary and in addition to.
Yeah, lots of flexibility there. One of the audience questions, what is the maximum number of requests and reply that can be launched to or received from your NOC? The NOC is external to, it's not the NOC inside of the cluster.
The NOC is external to, yeah. We don't, we're NOC agnostic, if you will, and work with you know, companies like Arteris that offer NOCs. I believe we support 48 outstanding requests to the NOC. It's just off the top of my head. I believe that's the correct number. But again, there's with the NOC, there's full coherency with the L2 cache with snooping. So, you know, if you have a memory out on the NOC or another cluster out on the NOC or a host processor, you can maintain coherency between whatever that is and the L2 cache.
Yeah, and so you connect through your ACE Lite interfaces.
Yeah, that's actually connected through either an ACE interface or it could be, well, it'd be ACE in that case, yeah.
Yeah, okay. And so there's a question on your coherency method that you use internally.
We use the protocol. It's a Mosey protocol. So, okay. Yeah, between the CPU cores and the L2 cache, yeah.
Sure. Okay. Question from the audience: will the hardware accelerators attached to the new cores have higher? I'm not sure higher bandwidth compared to what. Higher bandwidth load store. You said it's 128 bits per cycle. So.
Okay. Yeah. The bandwidth between the hardware accelerators and the interconnect is configurable by the user. That can be 64 bits wide up to 512 bits wide. It really determines how much information you can move. And of course, the limitation there would be primarily in what's designed into the hardware accelerator and how much data you can move and how fast. The 128-bit capability I was talking about is a load store capability that's built into each of the CPU cores so that you can move data very efficiently between the CPU cores and memory, or a hardware accelerator for that matter. But that's a little bit different than the capability that the hardware accelerators themselves would have, which is obviously very user dependent since they're the user's hardware accelerators.
Right. Yeah, and on that vein, there's a question about the accelerators, but I think it's up to the user. Is just do the accelerators support command response and interrupt FIFOs? I would think that's up to your customer.
Yeah, I think that's up to the customer.
Yeah. Okay. Somebody's not satisfied with 512 bits. Would like wider.
Sure, I am.
Wider load stores. So how about one of the potential customers wants to know how about that?
Mm-hmm.
2 cores.
Yeah, no, I by the way expect to see wider interfaces as we move forward. As I said just a few years ago, 64 bits for high-end applications. I'm talking about embedded applications, of course, seemed like enough. Then we went to 128-bit, then 256. And now 512 bits. And by the way, those are not just external connections, but also internal connections. So you can maintain the bandwidth inside of the processor as well. With that many cores, that becomes a significantly a large structure, I think is the right way to put it, even in a 7-nanometer process. And so it's very important to maintain and pay attention to the bandwidth inside of the processor so you don't stall any of the cores.
Sure. And then with a very specific question about the cache, does it support miss capabilities?
I don't know off the top of my head if it supports miss under miss. It's a very fully capable cache. Let me put it that way, which is a little bit vague, but there's a tremendous amount of capability, especially the L2. Of course, I think most of the watchers are aware the L2 cache controller is a large and very complex processor structure in and of itself. And we build a lot of capability into that. The L2 is 16 ways, so there's a lot of potential performance capability with, again, full snooping and coherency capabilities.
Good. Well, I think we're just about out of time, and I'm going to just throw in a promotion for ourselves. We will be covering these new HS cores and microprocessor report, and that article should be out in our issue for next Monday.